Today, we're going to dive into a revolutionary idea, a scientific mystery so radical, so out there, that it was actually rejected for decades before it completely changed how we see our own planet. This is the incredible story of Alfred Wegener and his theory of drifting continents.
You know, it all starts with a really simple observation, one you've probably made yourself. You're just looking at a world map and you can't help but notice it, right? Especially the way the coast of South America seems to just slot right into the coast of Africa. Well, it turns out that isn't just a coincidence. It's actually the very first clue in one of geology's greatest detective stories.
Now you have to remember, for centuries, the scientific consensus was that these massive continents were completely fixed. They were permanent features of the Earth, locked in place. The idea that they could actually move was just unthinkable. It was a planet-sized puzzle, hiding right there in plain sight.
But then, one man came along who dared to suggest the unthinkable, that the continents not only had moved, but that they were still moving. So let's meet the protagonist of our story, a guy named Alfred Wegener, and explore the truly radical idea he proposed way back in 1912.
What's so crucial to understand about Wegener is that he wasn't just a geologist. His expertise was all over the map: zoology, botany, physics, climatology. And this unique, multidisciplinary perspective, well, it gave him a kind of superpower. It allowed him to connect clues from totally different fields that all the specialists had completely missed.
So here was Wegener's big hypothesis. Hundreds of millions of years ago, he said all the continents we know today were actually joined together. They formed one enormous supercontinent that he called Pangaea. And this megacontinent was surrounded by a single vast ocean he named Panthalassa, which basically just means all water.
But how could that even happen? Well, to explain it, Wegener came up with a simple but brilliant concept. He argued that the lighter continental crust, which he called Sayal, was literally floating on top of a denser oceanic crust called Sima. The best way to think about it is like giant rock icebergs floating on a sea of even denser rock. And that was the key to how they could move.
Okay, so now that we've got the basic idea down, let's get to the really epic part of the story: how this massive supercontinent began to tear itself apart, setting the stage for the world that we all know today.
All right, let's just walk through this planetary transformation. About 225 million years ago, we've got Pangaea, totally whole and intact. Then, fast forward about 150 million years ago, and it makes its first huge split into two smaller supercontinents: Laurasia up in the north and Gondwanaland in the south. By 100 million years ago, things are starting to look a little more familiar as the continents keep breaking apart and drifting, eventually leading to the map we see today.
Now, a theory this big needs some serious proof, right? You can't just throw that out there. So Wegener basically became a detective, gathering evidence from all these different scientific fields to build his case. Let's open up his evidence files and take a look at the clues he presented.
The first and most intuitive piece of evidence was what the source material calls the jigsaw fit. I mean, Wegener just pointed out that the shorelines of the continents, especially South America and Africa, they just fit together with this uncanny precision, almost like they were once joined and then torn apart.
But Wegener went so much deeper than just shapes. Using radiometric dating, scientists found that ancient rock belts along the coast of Brazil were identical in age, a staggering 2 billion years old, and structure to rocks found in Western Africa. I mean, how could that possibly be a coincidence?
And the geological evidence gets even more specific. There are these rich gold deposits found on the coast of Ghana and Africa, and it turns out their source material is from rock formations over in Brazil. It's literally like finding two halves of a treasure map on opposite sides of the Atlantic Ocean, pointing to a time when they were one and the same place.
But then the biological evidence came in, and that made the case even more compelling. Fossils of the exact same species of ancient plants and animals were being discovered on continents that are now separated by thousands of miles of ocean. So the big question was, how in the world did they get there?
So let's look at the suspects. You have Mesosaurus, a small reptile that lived in fresh water. Its fossils are found in both South Africa and Argentina. But there's no way it could have swum across the huge, salty Atlantic Ocean. Then you've got the land dweller Lystrosaurus, which is found in India, Africa, and even Antarctica. And the fern Glossopteris is found across all the southern continents. The only logical explanation was that these lands were once connected.
So with an almost perfect coastline fit, matching ancient rocks, and all these fossils that made no sense otherwise, you would think the case was closed, right? But here's the crazy twist. The scientific community almost unanimously rejected Wegener's theory. Case dismissed.
And this really is the key question. Why? Why, in the face of all this compelling evidence, was the theory just thrown out for decades? What was the missing piece of the puzzle that Wegener just couldn't provide?
And here it is, the fatal flaw. For all of his evidence that the continents had moved, Wegener couldn't provide a convincing explanation for how they moved. He couldn't identify a force that was powerful enough to actually push entire continents across the surface of the planet. And this is a really important part of the story. The objections weren't just stubbornness. They were legitimate scientific criticisms at the time. The forces Wegener proposed, things like the tidal pull from the moon, were calculated, and they turned out to be millions of times too weak. And the image of these lighter continents literally plowing through dense oceanic crust just seemed to violate the known laws of physics. He had the what, but he just didn't have a plausible how.
But Wegener's story doesn't end in failure. Not at all. Because even though his theory was dismissed in his lifetime, he was ultimately vindicated by time, cementing his place as one of the great visionaries in the history of science.
And there's a really tragic element to this story. Alfred Wegener actually died during an expedition in Greenland back in 1930, so he never lived to see his revolutionary idea accepted. For decades after his death, continental drift was still treated as this fringe, almost laughable idea.
But this is where you see his true, lasting impact. Decades after he died, new technology, a lot of it developed during World War II, finally provided that missing mechanism. Sonar mapping of the ocean floor revealed these enormous underwater mountain ranges called mid-ocean ridges, and scientists discovered the seafloor was spreading outwards from these ridges, creating new crust and pushing the continents apart. Wegener's central idea was right all along. It laid the foundation for our entire modern understanding of geology, the theory of plate tectonics. He asked the right question, and that changed everything.
And get this, the process he first identified is still happening right now. As we speak, the continents are drifting at about the same speed that your fingernails grow. So it leaves us with this final fascinating question. If we could fast forward 200 million years into the future, what would the map of our world even look like?